Um, Hello, Eddie John.
Good morning, good evening, ma.
Good evening. So please, it's still like 7 minutes to 8. So let's just wait a bit.
Yes,
Others
ma.
they will
I
soon
already
join.
told them they are trying
Okay.
to join.
All right. Okay. Okay. Hello. Hello and welcome. It's exactly 8 o'clock now because I tried to start the meeting on time to enable you come in and all that, and waiting for it to be 8 o'clock because I said you people, we all agreed that was it, although for yesterday, 8 from 8, but yesterday wasn't convenient for me, so I had to shift it today to 8 o'clock. And now it is 8. So I will start when others are coming, they can join so that we can finish and all go and rest. So today is our 4th class. I think that should be module what? I know I think, well, okay, that is still module 1, unit 4, because this module 1 is so long, up to 6 units. It's still module 1, unit 4, and it is talking about the size of an atom, atomic size, atomic radius, because we measure the size of an atom based on the atomic radius. Everywhere is dark now. There's no light at my end, so you have to endure. So I will begin to share my PowerPoint now so that we can be very, very fast about this. Can you see my PowerPoint?
Yes, ma'am.
Yes, ma'am.
Okay, all right. So,
Yes,
okay, thank you. So that's the one you need for atomic radii, because we're talking about more than one radius. I'll just go straight to the point. You know, when we have an atom, and we now always depict the shape of an atom in a circular form, the way we've been, showing our shells and all that. So we always say that the distance from the center of the atom, which is the nucleus, to the outermost, to the electron in the outermost orbital or outermost shell, is the atomic radius. But then it's not just easy to define it like that. You just use the atomic radii or radius to just define the size of an atom. Because now you just don't have only atoms, you only have ions. You now begin to talk about its size, you now begin to talk about cation, anions, and the different bonds that are formed, because cations and anions come as a result of, in the process of formation of ionic bond, where this one will lose electron, one atom will lose electron, another one gains, they form charges, positive and negative charge. The charge will now attract, you have the ionic bond. There's equally the covalent bond. So it now means that the atomic radii is defined on the premises of the bond that is formed, that atoms form. So with that, we have about 4 types of, I use this picture to depict what an atomic radii should be, talking about the center, the distance from the center, which is the nucleus, to the electron. We call it the electron cloud in the orbital. But like I said, it's not just straightforward to define it like that. So atomic radii is defined based on the premises of the bonds formed, that atoms form. So with that, we have 4 of them. We have covalent radius, ionic radius, metallic radius, and van der Waals radius. This is year 1. So I will just take time to explain. If it's year 2 or year 3, I'm discussing it because I know they should have treated in the various chemistry courses per se type of bonding. Like now, even from our O level, we know that when we are taught Because even before you begin to choose course to say whether you're a science student or not, everybody does every course at the SS1 level. You will do everything, then later SS2, you begin to separate. You might say, I don't like this course, you drop it. I like this one, you go there. But year one, they will have taught you all this. And the basic foundation then that you want, they begin to teach you about atoms, the different particles, electrons, protons, and all that. Then the bond that atoms form. And they teach you that atoms form bond because they are trying to attain stability and all that. But I'm not going into all those grammar now. We're just interested in this. So I'm just trying, because for you to understand covalent radius, ionic radius, metallic radius, you have to understand the kind of bonds that atoms form. Atoms will either form ionic bond, covalent bond. Then the atoms of metals don't form ionic or covalent, they form their own, which is called metallic bond. Then we have the van der Waals forces, the weak forces. That one is formed between molecules, not between atoms. I will take my time to explain. Now, on the periodic table, the elements of group 1 and group 18 form ionic bond. The group 1 will lose electron to form cations and become, remember the last time we treated cations and anions. They will lose electron to become positively charged. The group 18, the group 17, rather, the halogens, they will lose electron to form, they will gain electron. They will collect electron from the group 1 because those ones need 1 electron for their orbitals to fill up. Then the group 1 will lose electron to this group 17. The group 17 will gain it. Because they have gained electron, they become negatively charged. They are now called anions. Why the one that lost electron that is now positive charge becomes cations. Those charge, those positive and negative charge will now attract themselves and form a bond. That's why they call it ionic or electrostatic bond of force. They form a bond by electrostatic force. So that is why those kind of compounds, that kind of bond, what is formed is compounds. And the compounds will dissolve in water and begin to conduct electricity and all that. Then you now have, likewise, group 2. Group 2 will equally lose the electron to the group 16 elements. Because the group 2 has 2 electrons in its valence shell, then the group 16 needs 2 electrons to fill up. So the 2 of them can combine and all that. So group 1 and group 2, group 16 and group 17 form ionic bonds. Then the ones from group 3 to group 15, those ones form covalent bond. I'm not talking now about those ones in the middle, those transition metals and all that. I'm removing them out of this and all that. So I'm just talking about group 1, group 3, 4, 5. Then from where you begin to now have, I think 14, 15, 16, 14, 15, and all that. Those ones, because the group 3 elements, they find it difficult to lose 3 electrons at a whole. They can't lose 3 electrons. And for the group 15, they need 3 electrons to fill up. They are looking for electrons. Since the group 3 cannot use electron, or even when they want to form a bond, let's say group 3 wants to form a bond with group 3 itself, then the group 15 wants to form a bond with itself. It cannot, where you have like that group 15, you have nitrogen, silicon, phosphorus, and all that. It cannot, okay, it's group 16, you have silicon, phosphorus in the group of oxygen. But in the group of 70, the group 15, where you have nitrogen, those ones cannot lose electron. They need to gain electron, and the group 3 are not willing to give it to them. So what they do, there's a mutual agreement. they would now share their electron. As they share their electrons together, this one brings that 3, the other ones bring that 3. They will now share it, and by that time, as they do it, the way you were taught in your O level, they will now have the right number of bonds they should have in their valence orbital or valence shell and become stable. So that sharing, as we're taught from secondary school, that covalent bond involves the sharing of electrons by atoms of an element. So as they share that electron and bond together, they form a bond. And that electrons, those electrons that are shared between them, are held to the nucleus, and that keeps them in place. So we're trying to say you have ionic bonding, you have covalent bonding. Then metallic bonding, it's the one that is formed by metals. Metals are solid. It means it has every metal. Let's say, for example, maybe zinc metal. What you see in a zinc that makes it solid is many of its electrons that have come together and compacted together and are bonding becomes a solid. Because for any compound or molecule to be gaseous, it means it's just single entity. But once it begins to come together, the atoms begin to come to. For instance, let me use the water molecule. Water is H2O. Water will exist as a gas. It will exist as a liquid. It will exist as a solid. You should have asked yourself why. Because the gaseous water, H2O, is just a single thing, H2O. But this H2O, which is a molecule, can begin to bond with other H2Os. As they begin to bond, as the bond increases, each of those, you have so many molecules coming together to bond. It would, because the length of the bond is increasing, as the length of the bond is increasing, it will start becoming liquid, and just like that. So I'm using it, coming back to metals, to show you that it's not just one atom that you will have there. You have several of the atoms of that zinc. I'm using zinc as a metal. Several atoms of zinc that have come together and are bonding together, giving it that solid form. So in a metal or in a metallic bond, you have several atoms of that one, that same, just that compound. I'm still using zinc. If it is sodium, it will only be sodium. It will not be bonding with any other element, but just its own atom, many of them coming together, joining together. And as it increases, to give it that solid form. So for you to understand metallic bonding and all that. Now you have the van der Waals forces. The van der Waals forces, example is like the one that exists between water molecule when each water molecule, each H2O begin to join together to give you a liquid. What is holding them together is van der Waals forces. Van der Waals forces exist between molecules, holding molecules together, such as hydrogen bonding, dipole-dipole attraction. I will stop at that. So we call those ones. You see covalent bond, before I will now come back to covalent radius, covalent bond, ionic bond, metallic bond. These are what we call interatomic bond between atoms, between two atoms, and not between atoms. But now when atoms have come together to form a covalent bond, it has formed the molecule, but the molecule can now begin to bond again in the case of van der Waals forces. So van der Waals forces is an example of what we call intermolecular bond and all that. So having explained that, we will now come, because you need to understand it. I'm trying to refresh you. You've done this in secondary school. I'm trying to refresh it for you to understand where we're going to: covalent radius, ionic radius, metallic radius, and all that. Why we're saying you can't just describe the size of an atom just saying the distance from the center to the outermost electron in the outermost shell So now we want to go into what is covalent radius proper. Now, covalent radius can be formed by the same atom, two like atoms. For example, it can be formed between two hydrogen atoms, hydrogen plus hydrogen. H2 gives you hydrogen molecule. Can be formed between oxygen, two oxygen atoms. These are same atom. So these are called homonuclear atoms, homonuclear molecule, because they are the same atom. But whereby you now have the bonding, the covalent bond. I'm not just talking about ion, but right now have the covalent bond between two different kinds of atoms. For example, between the one you find in water, hydrogen and oxygen, that is a hetero. Hetero, you know, hetero means different. Homo means the same. So homonuclear means from bonding from the same, covalent bonding from the same atom. Then hetero from different, like as you have in water, hydrogen and oxygen. These are two different atoms. Then you can have, as I have here, carbon, a bond between, okay, there's somewhere I showed that one later, a bond between carbon and chlorine to form a covalent bond to give you carbon chloride. That is another example of a heteronuclear, because these are two different atoms. Why I'm saying this, because this covalent radius have two different ways of finding it. For the one that is a homonuclear covalent bonding, then for the one that is for a heteronuclear bonding. Now, for a heteronuclear molecule, like I use example here, chlorine, two chlorine atoms sharing their valence electron to form a covalent bond to give you the chlorine molecule. Now, let me come to where I drew, I believe I drew, okay, this is it. So I use this as an example. This is, the first one is one chlorine atom, this one is another chlorine atom. Then, as they form this bond, this electron is shared between their edges here, as my cursor is pointing. Now, you have the center, which is the nucleus. This one too is the nucleus. So, from the center of the nucleus of one of the atom to the nucleus of the other atom is the bond length. This is the bond length. So half of this distance will give you the covalent radius of each of these chlorine atoms. So that will take us to the definition of fluorine atoms. Now, let me just read what I do. I say, when a covalent bond is present between two atoms, the covalent radius can be determined. When two atoms of the same element are covalently bonded, e.g., two chlorine atoms, the radius of each atom will be half of the distance between the two nuclei, because they equally attract the electrons. Thus, the covalent radius can be defined as 1/2. That is half, even if it's like, don't put 1, but just know that it's half. Can be defined as half of the distance between the nuclei of the two like atoms bonded together by a single covalent bond. We're not talking about this when you have a double bond or a triple bond. We're talking for a single covalent bond. So we're saying that this covalent radius, the way you determine the size of a chlorine, because the size of, we're trying to talk about how do you determine the size of an atom. And we say, because I want you to understand what we're talking about, the size of an atom can be determined from the radius. And for you to know the radius, you have to understand the bonding, which is what I've just explained. So the size of the chlorine atom, that's what we're saying, determined from this covalent radius. It is half of the distance between the nuclei of the two of two like atoms. You cannot say two like chlorine atoms, but we're not generalizing for all atoms that form covalent bonds. And we have been able to tell you atoms that will form covalent bonds. Those ones from group 3 to group 15 will form covalent bond, excluding, I'm not talking about those transition metals and inner transition metals when we looked at the periodic table. Remove those ones in the middle, but from when you remove those ones now from that group 3 to group 15, those ones will form for you covalent bond. Then when any of the group 17, like chlorine is in group 17, if it's bonding with itself, it's going to form a chlorine, it's going to form a covalent bond. And if it's bonding with any element too from group 3 to that 5 to 16, it will equally form a covalent bond. It's only when it's bonding with group 1 that it will form an ionic bond. So let's move ahead. I've already defined this, and I've been able to use this to give you. This is this is the first nucleus, this is another nucleus. So you have 2 nuclei. This gives you the bond length anyway. So this is the nucleus. So the distance between 2 nuclei covalently bonded by a single covalent bond, how the distance is covalent radius. So with that, okay, thank God it brought light where I am. Pray that they would leave it for some time to the end of this class at least and all that. So that is that. Then I said, for example, the internuclear distance between, because mathematically, they can give you the internuclear distance between 2 homonuclear atoms and ask you to determine the covalent radius. If you know that the covalent radius of each of those atoms is just half the distance, you just divide by 2. So we say, for example, the internuclear distance, we represent it by R. The compound we're talking. Which one? Who is this one? It will be Kelechuku or whatever. You better mute yourself. Maybe you're just even just joining. Better just mute yourself. So I say, for example, the internuclear distance RCl between the 2 chlorine atoms is 198. So we're saying that this, you can see it here, this internuclear distance, internuclear, because we're talking about nucleus, so inter between the 2 nucleus is 198 pm. Pm is picometer. So for you to get the covalent radius of a chlorine atom, then you divide by 2, which will not give you 99 pm, which is picometer and all that. So we say, for example, the internuclear distance between the 2 chlorine atoms is 198. So the covalent radius of chlorine is equal to 99 picometer. So having explained that, we go to this one I just described is for a homonuclear. Now you have the case where I said when it is between 2 different atoms that are coming together to form a covalent bond to give you what we call a heteronuclear diatomic molecule. You will not get the radius just by halving like that. It's a different thing. The only way to get it, first and foremost, because for most of the covalent bond for heteronuclear, the internuclear distance have been determined. So for a covalent bond existing between a compound as carbon chloride, between this carbon and chlorine, the internuclear distance between the carbon atom and the chlorine atom, who is that one now? Obi Kelechuku. Some of these people just don't respect themselves. Obi Kelechuku, or whatever is your name. Okay, so I will have just removed her from this place. I just decided just to leave her. Some of these people can be very foolish and all that. So we're now saying that for a heteronuclear diatomic molecule, such as carbon chloride and all that, and for similar ones like that, that their bond, their internuclear bonds have been determined. So for you to now get the atomic radius, say for example, of this carbon here, what you will do, knowing the internuclear distance and knowing the atomic radius for chlorine, you just simply subtract from the internuclear distance the atomic radius for chlorine. That will now give you that of carbon, because the internuclear distance is an addition of the covalent radius of carbon and the covalent radius of chlorine. So that is how, for a heteronuclear distance, the covalent radius can be determined. We now want to go to, I just use this one to just give an example. I say it is possible to calculate the radius of one of the atoms in the heteronuclear atomic molecule. It's just what I've explained anyway, but I use this one here. For example, I use silicon chloride, whose bond length or internuclear distance is 193 picometer, and the covalent radius of carbon determined already is 77 picometer. So I say you can calculate the covalent radius of even chlorine. You can calculate the covalent radius of silicon from it, knowing, since we know the internuclear distance between the silicon element and that of carbon, that is 193 pm, then, and the covalent radius of carbon is 77. So by the time you subtract, you have 1116, which will now give you the covalent radius for silicon. So we have looked at how you can determine or define the covalent radius for a covalent compound, and how you can determine from there for you to know the size of an atom. Then you now have for ionic radius. This one has to do for ionic compounds and all that. Now, for the ionic radius, we said ionic radius is distance from the nucleus to the outer edge of the electron cloud of an ion. The definition is different from the covalent radius as we know, because now you can have a cation, you can have an anion, depending on the type of ion that is formed. So we're saying that the distance from the nucleus to the electron cloud, because the electron normally orbits, as it orbits, it will be spreading and having cloud. So where the last cloud gets to is what we're talking about. So the ionic radius is distance from the nucleus to the outer edge of the electron cloud of an ion. I said in simple terms, ionic radius is the distance between the nucleus and the electron in the outermost shell of an electron, to make it simpler for you. Ionic radius is normally determined by an instrument called X-ray crystallography, using what we call X-ray diffraction patterns. But that is not what they want you to learn here, because that one is for people that are in third year chemistry and all that. So the simple thing, we're just trying to say that ionic radius is determined using the ionic radius of ionic compounds is determined. Most of them have been determined using this equipment called X-ray crystallography, or the method of X-ray crystallography. So now we know that we have already told you the kind of compounds that form ions and all that. We're now looking at, for example, like sodium chloride. Sodium is in group 1, chlorine in group 17. So when they bond, they will give you ionic compound. You now have sodium chloride, like the common salt you use at home. We said the distance is the sum of the radii of the sodium ion, which is a cation, and the chlorine anions. That is let me read this. I say ionic radii is usually evaluated from the distance determined experimentally between the centers of nearest neighboring, usually using crystallography. Because in a crystal lattice, ionic compounds form what we call crystal lattice. And in that crystal lattice, these ions are packed, having different shape. They are packed together, close to each other. You see the chlorine atom. I'm using now sodium chloride. The sodium chloride will be packed, will be next to the chlorine atom, and just like that. So that's what I'm trying to say here. That say, for example, if we wish to estimate the ionic radius of sodium, we may measure the internuclear distance between sodium and chlorine ions in the sodium chloride crystal lattice. This distance is the sum of the radii of sodium ion and chlorine ions to get the ionic radius. So sodium chloride or sodium ion or chlorine ions, can't see what is there. We divide the internuclear distance according to atomic size. What we're just trying to say is that using this equipment called X-ray crystallography, you can determine the internuclear distance between the atoms, the ions that are bonding together electrostatically with their positive and negative, whatever, to give you the ionic compound. So you can determine their internuclear distance and all that. Then, for you to get the size of any of the ions you're talking about, just as we did for a heteronuclear, because these ones are normally heteronuclear, knowing the internuclear distance. If one of the ions is known, is simply to subtract it from the internuclear distance, because we are saying the distance is the sum of the radii of both of those nuclei, the cations, both of those ions, the cations and the anions. For example, here the sodium cation and the chlorine anion that form the sodium crystal lattice. So once this equipment is used to know the internuclear distance of these two ions that are bonded together in the ionic bond, for you to now get the size of one of the radius, because radius means one. Then when we talk about radii, we're talking about the two. So radii, for you to know the ionic radii of any of these ions, if you just do what you do in case of heteronuclear covalent radius, you will be able to get the size of that particular ion you're looking for. But one thing again, we need to know that for cations, their size are usually smaller because they lost electron compared to the anion and all that. So that's that about how to determine the size of an ionic radius. And we have been able to define what ionic radius is. That ionic radius is distance from the nucleus to the outer edge of the electron cloud of an ion. So we go to the next one, which have to do with, okay, I was just trying to say two ionic radii of two types, cation radii and anion radii. I've already explained that. And I've already told you that the cation is smaller compared to the bigger one, so we're not going into that anymore. We want to look at metallic radials. I've already explained to you, when I was trying to explain to you the different types of bonds that atoms can form, when I now talked about metallic bonding that exists in metals. Now, since we have so many of the atoms of that same comp of that same element. For example, zinc, you only have so many atoms of zinc that are packed together in a sphere like that, packed together, bonding together to give you that solid called the metal. So for the distance, now we said the distance or the metallic radius is defined as 1/2 of the distance between the nuclei of two adjacent metal atoms in the closed pack. We have said that the atoms of these metals pack together. They are just, you know what is adjacent? Next to one another, beside one another, if we use it like that, next to one another. So remember that these atoms have nucleus and all that. So as they are next together, their outermost electrons are bonding together. The other one too is packed to the other one. They are packed like that. So all of them, the outermost electron, they are the one that so far they are adjacent, as they are the two adjacent, their electrons will be together, just like that, and it continues to go. So we're saying that metallic radius is defined as 1/2 of the distance between the nuclei of two adjacent metal atoms in the closed packed crystal lattice. That is what is what metallic radius is. So we now say, this we have some things covering here and all that. I wanted to read out what is here and all that. But, well, I think what I said, the internuclear distance between two adjacent sodium atoms, because sodium is a metal in a crystal, in the sodium metal, is 382 picometers. So metallic radius of metal, of sodium metal, is 1/2 of 382, which is 382 divided by 2. That is 191. Who is drawing this thing here? Who is this baby that I have in this class? Yeah, you people just be behaving funny. Don't allow me just leave your class one day and all that. Somebody just came and started, you are not listening, you're just doing what I don't know and all that. What kind of thing is this? Even if it's a baby. And maybe I should leave the teaching for you so that you begin to teach it yourself. So we have defined what metallic radius is. I've explained to you what is metallic bonding and how it comes about. So many atoms of that same element bonding, being together as they are packed together, the bond. And we're saying because these atoms have nucleus. So as they are adjacent, the two that are adjacent together, you have another two. All of them are packed together. You can have them, we call them sea of electrons. Many of them, many. But two would be adjacent to the other. As that two are adjacent, another one will come and be adjacent to that one, forming the third one, the fourth one, just like that, packed many. But we just define it from two, that metallic radius is defined as 1/2 of the distance between, so I use this, 1/2 of the distance of the nucleus of two adjacent metals, two adjacent atoms of two adjacent metals have the distance of their internuclear distance, 1/2 of it as you have it. That is metallic radius. So metallic radius is defined as 1/2 of the distance between the nuclei of two adjacent metal atoms in the closed packed sphere. And we're saying, if I'm using an example here, if you have that the internuclear distance between two adjacent sodium atoms, it can be a zinc atom, but I'm using zinc atom because I'm using sodium here because sodium is a metal, is 382. So if you want to get the metallic radius, because this one is two adjacent. Now, if you want to get the radius of the sodium metal, just one of the metal, one of the atoms, which is what we're talking about. You just half the distance to give you 191. We'll now want to go to van der Waals radius. Eddie John, ask your question quickly so that I can go to the next one. I can see you raise.
I just wanted to say that you should show that diagram, the diagram of the metallic radius again.
This is what I showed. So this is metal X and metal X. The metal X can be any of the metals. That's why I didn't say X and Y, to show you that they are the same atom, because we said it's the same atom that of the same element, that because if it is zinc, it will be zinc all through, all the zinc, or everything there will be zinc atom and all that bonding together. So we're saying this is the internuclear distance. These are two adjacent. You know, when something is adjacent beside each other. So like this, you have another one. If it's a typical, if I'm to start drawing a typical metallic bonding, you see another atom bonding here, all over. It will just fill up everywhere. Many of them. That's why you have it that is solid and strong like that. But we're just saying between two adjacent. These two are adjacent. So, and this is their nucleus, because every atom have a nucleus and all that. So the internuclear, the two nuclei and all that, the internuclear distance, half of it is known as metallic radius. So metallic radius is half the distance between two adjacent metals that are bonded, two adjacent atoms, metal that are bonded together. So we want to go to van der Waals radius. I've already told you what van der Waals forces or bonds are. It is formed between molecules. Now, for here, I'm using example, the chlorine molecule. Chlorine molecule exists as a gas. Chlorine gas is a molecule. Two chlorine atoms giving you Cl2. Every molecule is made up of two atoms. So this one here, this chlorine bonding to this chlorine, forming a covalent bond here, gives you the chlorine molecule. Now, I've told you about, I said that the van der Waals forces is formed between one molecule and another. I even use water to explain to you. If it's just one molecule, it will be, that's when you have gas. If it's a liquid, you have that many of the water molecules, H2, are bonded together and all that. So now this one is solid chlorine. We know that chlorine exists as a gas. So just the chlorine molecule Cl2 will exist as a gas, but you only have solid chlorine. And it is when many of the molecules now bond together, it will now solidify, because as the bond length keep on increasing, it will change from liquid to solid and all that. And for each of these chlorine molecules bonding together, you have a van der Waals force. This is not a hydrogen bond. Like in water, you have what the van der Waals force is called hydrogen bonding. You must have heard about it. That one is formed between hydrogen atom and electronegative atom like oxygen and all that. So, but this one is what we call dipole attraction. But we're not here to be discussing bond, just van der Waals radius. So now, since you have seen that these ones, they are adjacent to each other and bonding, you have another one like that. So that will now, let me know, I'll go back to the definition of van der Waals radius. I say van der Waals radius is half of the distance between the nuclei of two atoms belonging to two adjacent molecules in a crystal lattice. Half of the distance between the nuclei of two atoms belonging to two adjacent molecules. Look at what I'm saying. We're talking about half of this distance between this chlorine atom and this chlorine atom. Half the distance between two atoms belonging to two adjacent molecules. These are two. This is a molecule. This is another molecule. They are adjacent to one another, next to one another. Then these adjacent molecules, we have their atoms. One atom from it, one atom from it, bonding together by van der Waals forces to keep these molecules joined together to give either a liquid or a solid. So have the distance between these two atoms belonging to two adjacent molecules. So I go back to that definition. Half of the distance between the nuclei of two atoms, we are talking about these atoms, but these atoms belong to two adjacent molecules in a crystal lattice. And I told you van der Waals forces will bring molecules together and make them go off being gas to either liquid or solid. For this, for example, this chlorine gas with these van der Waals forces that they are packed together makes it become a solid and all that. So that is that about the definition of this atomic radius. And you have to understand it by the time you understand this bonding in atoms, in molecules, so that you begin to know when we say half the distance between compounds that are covalently bonded together that by single covalent bond and all that. For equivalent radius, the ionic radius, then the metallic radius. You have to understand the bonding for you to understand how these atoms in metals packed together and adjacent to one another. So have the distance between the nuclei of the two adjacent atoms in a metal. Then for equivalent bond, we have explained that. So knowing that now, we want to look at another thing that is in that your book, I mean your course material, is factors affecting the atomic radius. But before I go further, any questions so far so that we can address these before I now go into this other one?
Hello, ma.
Yes, who is talking?
Yes, ma. This is Ifeoluwa, ma.
Okay, ask your question.
Yes, ma. When you were talking about ionic radius, ma, you
Yes.
said we have 3 types of ionic radius. That we have cation radius, anion radius, but I did not.
I didn't tell you 3. It's 2. Cations and anions. You only have, how many ions do you have? You only have 2 types of ions: cations and anions. Cations, the ones that have lost electrons and are positively charged. Then anions, the ones that have gained electron and are negatively
They are negatively charged.
Yes, so it's only 2 anions.
Yes,
Two
ma.
ions, sorry.
Okay, ma. But you said something when you're talking about the cation radius that is smaller. So I did not hear that part.
I say it's smaller in size because it loses, you know, the atom has lost electron. So the other time when I was showing, there was something I was showing, what was that? That was the last topic. And you see when it loses electron, even don't worry, as we go further, because these factors are affecting it, you will see what's going to happen along, you know, all this kind of something. When I begin to talk about it, I don't know who is drawing this nonsense up and down here. Who is this child that I have in this class?
Thank you very much, ma.
Okay, any other question?
Okay, ma. You talk about covalent bond.
Who is talking?
Hello, ma.
Is it Usman?
Yeah.
Okay.
You talk about covalent bond.
Yes.
Covalent bond. The fake example we give the chlorine. You call harmonious. The second example is silicon and example of covalent bond by Kikabai.
Hello, ma. What happened? I'm listening.
The first example.
Hello, ma.
No, let him finish talking, please. Yes, Usman, I'm listening to you.
Okay, the first, I talk about covalent bond, covalent radius.
Yes.
You give the first example. You say the silicon. I need to know homogeneous and heteros da kika kira.
Okay, homonuclear and heteronuclear.
Yeah.
You know, homo means the same. I'm using English now. Homo means the same. Hetero means different. So when I say homonuclear, it means the atoms are the same, like chlorine and chlorine. Chlorine atom and chlorine atom. So these are the same atom. So it will give you a homonuclear covalent bond. Okay. Then I now said you equally have a heteronuclear covalent bond whereby you have two different atoms. For example, carbon is a different element. Chlorine is a different element. So when they bond together, they will form what we call a heteronuclear covalent bond. That's different atoms coming together to form a covalent bond. That's what it means.
Okay, understood. Yes. Thank you, ma'am.
You're welcome. Hawa, you wanted to talk before. If you're not talking, or more Bolanle Rachel, you can talk. You can ask a question.
Good evening, ma.
Good evening. Welcome.
I am kind of confused at the point where we said chlorine equals to 198 PM. What does PM means?
I say it's picometer. That's the unit. For example, remember that's the unit for internuclear distance. That is still the same as bond length. You know, anything length, anything distance has unit. For example, in road, you know, what's the distance? Is it not meter or kilometer?
Kilometer.
Is it not?
Yes.
It's the same thing. You can either use kilometer or meter, depending. Okay. So we're talking about bond length or internuclear distance. We're talking about distance. So, but because this is a very minute distance, so that's why we said it's a picometer. It's not a meter. It's not meter. It's not kilometer. So, but because of the size, small, so it's picometer. So that's the unit for bond length or internuclear distance.
Okay, thank you, ma.
You're welcome. Any other questions? Otherwise, okay. So let's move ahead. Yes.
Please, ma, I'm sorry, ma. I want to ask another question, but it's not related to what we are doing, ma.
What is that?
Yes, ma. In our outline, in our material, there are some TMAs there. There are some questions that are there. So I want to ask, ma, are we to do it and post it somewhere, or is it just for us to practice?
TMA.
Like there are some questions. There are some questions under our materials.
Okay, your course material.
In our course material.
That's your course material now.
Yes.
It's for you to use it and study and help yourself.
Okay, it's not that we are submitting.
No, it's your practice question.
Okay, ma. Okay, ma. Thank you very much, ma.
You're welcome. Then, okay, so let's move forward. We want to look at factors affecting the atomic radius. There are factors that affect it. The factors that affect the atomic radius, number one, we have the principal quantum number, which is the principal energy level. Remember when we were talking about the electronic distribution, we mentioned the shells, then that inside the shells, you find the orbitals. So now, the shells, of course, you distribute the electrons inside the orbital and inside the shell. So as a principal energy level, see, I want you to understand this term. So far, you're at this level now in the higher institution doing these sciences. You know, in the secondary school, they just remit you to shell and orbital. But shell, too, another name for it is principal quantum number. So that when you hear that, you understand, because that is what is in your course material. So the principal quantum number, which is the same thing as the principal energy level, or shell, the way you have learned from the secondary school. We're saying that as this shell increases, the outer electrons get farther away from the nucleus, and hence the atomic radius generally increases. That's just every other grammar there. I'm not looking at it, but this is just what I'm saying. So let me use this to give you example using this period 1. And this shell using group 1 elements. Now, these are group 1 elements. To check your periodic table, when you go to the group, you see group 1. The first element you're seeing there after hydrogen is lithium. You now have sodium. You have potassium. Then you continue to go down till you get to the last element, but I'm just stopping at this last 3 because even this PowerPoint will not take to the 4th one. So if you watch this shell, you will see that as you're going down the group, the shells are increasing. The shells are increasing due to increase in atomic number. This lithium has atomic number of 3. This sodium has atomic number of 11. Potassium has an atomic number of 19. Because we have learned the other time that each shell has the maximum number of electrons you take. Once it gets to that maximum, the electron will go to the next one. Now, the first one we know takes a maximum of 2. So it means since this lithium has atomic number of 3, after the 2 goes here, the next one will go to the other shell, which is the K shell. Then, for this sodium, 11, atomic number is 11, so it means the number of electrons is 11, because we said from the other class, the number of protons, which is the atomic number, is the same thing as the number of electrons. So this takes maximum 2, this one maximum 8, then that gives you 10. The remaining one goes to a 3rd shell. So you have moved the weight, has increased from 2 shells to 3 shells. Then this one now, you can see it has 4 shells. This one's, the first takes maximum, the second, the 3rd, then goes to the next shell, giving you 4 shells. So you can see as you're going down the group, the shell increases. And we are saying, what we're just trying to say, I'm just using this to give an example, that as the principal quantum number, also called the energy level, the principal energy level, also called the shell. So let me just use the shell. As it increases, the atomic radius increases because the valence electron is moving away from the nucleus. Because the electrons in the outermost shell is always attracted to the nucleus, because the nucleus is positively charged, while the electrons are negatively charged. And you remember from your O level, unlike attract each other, while like, if they are like charges, they will repel each other. So positive will repel, negative will repel. But unlike, because this one nucleus is positive, the electron is negative, they will attract each other. So every electron is revolving around the shell. If not for the attractive force of the nucleus, it can fall out of place. So what keeps it revolving is the attraction of the nucleus to that electron. But now, when we have what we call inner screening effect, the inner electron screening, it's just, for instance, now, you have persons, maybe you line up persons, let's say 5 persons, you bring a torchlight and you shine in the dark. If you look at it, you will see that that torchlight, before it will get to the last person, it will not really get to it very well, because the first person would be shielding, then the second person said the light will get more to the second person, and in that order, the last person might not even just receive minute, because those people that are in between that torch and the last person there are shielding it, are shielding the light from getting like that. It will shine more on the first person, the second person, then the third person is less. So those people in between that torch and the last person, they are shielding it and all those things. So it's the same thing. I'm using it, that's an analogy I'm using to explain this thing. This charge, the positive charge of the nucleus, these inner electrons shield it to some extent from getting to the valence electron. So as this shells are increasing, the valence electron is getting farther away from the nucleus. So the attraction is less. So the ionic radius will just increase based as the shell is increasing. So as you can see here, you can see the distance of the nucleus, the atomic radius increasing, because we're talking about from the distance from the center to the outermost one and all that. So it's increasing like that. I want to, this other one, we're talking about effective nuclear charge. And I said effective nuclear charge, which is known as Z with the asterisk, is the amount of positive charge felt by the outer electrons in an atom. That's what I'm talking about as per the charge of the nucleus, the positive charge getting to the valence electron, the electrons in the outermost shell. If there's not much shielding, then the attraction of that positive charge to the nucleus will be much. It will now draw the electrons close to the nucleus, thereby reducing the size of the atom. So I said the second factor affecting the atomic radius is effective nuclear charge. Effective nuclear charge Z star is the amount of positive charge felt by the outer electrons in an atom. The magnitude of the effective nuclear charge determines the magnitude of the force of attraction exerted by the nucleus on the outermost electrode. The greater the magnitude of the effective nuclear charge, the greater is the force exerted by the nucleus on the outermost electron. Hence, the electron cloud of the outermost shell is pulled inward to the nucleus, and consequently, its distance from the nucleus, that is atomic radius, will decrease. I said the effective nuclear charge is actually less than the actual charge of the nucleus of an atom. That's the way it is in your course material, but I'm only just bringing it out to explain. The actual charge of the nucleus is different from the effective nuclear charge. Because you might see some of these questions, so I just want you to understand it. Now, the nucleus has its charge, the positive charge, depending on the number of protons. Just as I use this torchlight and persons, if you have people blocking and all before the last person, let's use that last person as the outermost shell where the electron is. If you can think, you'll see that the light, the torchlight, as you shine it will be more on the first person, the second person, then the last person. The magnitude that the first person, second receive will not be like that. So those first, second, and those inner ones are shielding that light. So that is the way it is. Now, the actual charge from the nucleus, that's the actual charge. But the effective nuclear charge, we're saying that is the real charge that gets to the valence electron. And valence electron we're talking about outermost electron. So the electron in the outermost shell. So the actual charge from the nucleus that gets to it, that is what is known as effective nuclear charge. So we are now saying that this effective nuclear charge can determine the size of an atom. It can either make it reduce or it can make it big, large, depending if there's so much shielding by inner electrons that are now receiving more of the charge than the valence, receiving more of the attraction than the valence electron. So it's just little that gets to the outermost electron. So it's less. The size of the electron can now be like that as more atoms are added. But if you don't have much inner electrons, then a lot of charge will get to it and it will be pulled inside, reducing the size of the atom. We're going to see that because this one we looked at, we're looking at down the group as you're going down the group. Remember, for elements. Elements, you have group and you have period. So I use the group 1 element to explain this. So we want to look at using the period 2 elements. In that period 2, you have lithium, beryllium. If you can see what my cursor is showing, you have lithium, you have beryllium, you have boron, you have carbon, you have nitrogen, you have oxygen, you have fluorine, you have neon, going like that. So I draw them like this again. They're using shell to distribute their electrons. You have lithium, 3 electrons. As you're going is increasing. This beryllium is 4 electron, boron 5 electron, carbon 6 electron, because the number of protons for lithium is 3, the number of protons for beryllium is 3, the number of protons for boron is 5, and that. And we have said the number of protons and electrons are the same thing. You can see that, yes, the electron is increasing, but it's not being added to another shell. It's entering the same shell. Now, as you go from beryllium, which is 4 electrons, to the one that has 5 electrons, is still entering into the same shell. As you go to carbon, it is simulating that number of electrons is increasing, but it's entering the same second shell. So you don't have any inner shell or additional shell formed, so that you don't have any shielding effect of inner electrons. So now the nuclear charge is increasing. As it's increasing, and less inner shielding of the inner electrons, so the outermost electron receives a lot of pulling from the positive charge of the nucleus, and now draws those negative charge of the electron, draws it closer to the nucleus, thereby reducing the size of these atoms. So across the period, atomic size increases. Sorry, down the group, atomic size increases. But across a period, atomic size reduces because of what I've explained to you. So this is just what I mean. I say down a group, the number of principal energy levels increases. So there is a greater distance between the nucleus and the outermost orbital. This results in a larger atomic radius. Using the group 1 element as an example, that's what, just what we have used before. So you see that the shell is increasing as the number of electrons increases. So taking the valence electron further away from the nucleus, from the attractive force of the nucleus and all that, so that it receives much less pulling. So the distance increases as the electrons or the shell is in the principal, the shell is increasing, but across, you don't have additional shells. So the nuclear charge is much on the valence electron, and the atomic radius decreases. So with that, we have come to the end of this class of Module 1, Unit 3. If you have any question, you can ask. If there's no question, we call it a day. Francis Peter.
Good evening, ma.
Good evening, welcome.
Thank you. Please, ma, is proton the same thing as atomic number?
Yes. That's what we've been saying, that atomic number is the same thing as proton.
Okay, ma. Thank you, ma.
You're welcome. Any other question? So that we can call it a day. Eddie John.
Good evening, ma'am.
Good evening, welcome.
Yes, ma'am. Thank you, ma'am, for the lecture, ma'am.
Oh, okay. I
Please,
was calling Eddie John, but anyway, go ahead. After Eddie John, we'll talk. Yes, go ahead.
I'm sorry, ma. I joined the class so late, ma. Please, are you going to send the recorded version of the class?
Mm-hmm.
Oh, thank you so much, ma. God bless you, ma.
You're welcome. So, Edidion.
Good evening.
Yes, ma.
ma'am.
Thank you.
You're welcome.
So ma'am, you said something about the principal quantum number being the same thing as the energy level.
And the same thing as shell. You know, for one word, they can have different names for it. So is that the way? I don't want to just be using shell, because in your course material, it is written there, principal quantum number, so that you know that that principal quantum number they are writing is still the same thing as shell, and it's still the same thing as principal energy level. That's why when I come to teach, I try to just help you to understand, to know that when they are saying this principal quantum number, they are still talking about shell. So it's another name for shell is principal quantum number, principal energy level.
Thank you very much, ma'am.
You're welcome. So I guess there's no other question. So we'll stop here, and we'll meet during our usual class on Tuesday, 5 to 6. And like I've said, throughout this class, that is that same link and passcode that we'll be using. Good night and have a blessed weekend, and I think
All right, thank
of the
you.
Independence celebration.
Thank you, Independence.
All right. Thank
Thank
you,
you,
ma'am.
ma.
Bye.
Thank you. Goodbye.
Bye.
Good night. Okay.
Happy Independence.
No go wish me happy
Same
Independence.
to
Because
you.